Imagine a future distant from human memory when the sun will no longer be content with its role as our faithful companion. The air quivers. A distant globe becomes a blazing wall of light. The blue dawn turns into a sea of fire, its waves crashing into the sky. Mountains and seas vanish in a flash of heat. Where night once ruled, now not a single shadow remains. Over millions of years, the core of the sun will expand, and each sunrise will bring us closer to agony. One day, there will no longer be a glowing horizon, and everything will simply burn. Soon, this fiery sphere will extend beyond Venus, beyond Earth itself. Rock will liquefy, oceans will boil, and the final breath of life will fade beneath the impenetrable flame. Gravity will pull our wounded world inward into the gaping maw of our aging star. This is the inevitable fate of our star and every world that orbits it. In this final act, the sun will take its children with it. It's not a question of if, but when. The story of our system's end begins here. Four and a half billion years ago, in a quiet region of the Milky Way, a giant molecular cloud lay dormant. Its gas, made up of hydrogen, helium, and dust, had been seeded by previous generations of stars, remnants of supernovae that scattered heavy elements like carbon, oxygen, and iron throughout the cloud. When the shock wave of a supernova struck the cloud, it compressed the gas to a point where gravity took over. Dense clumps formed and collapsed, spinning faster as they shrank. In the center of one such clump, pressure and temperature increased until a protostar was born, an object still shrouded in dust, faintly glowing in infrared light. The matter from the surrounding disk spiraled into the young star. Jets of hot plasma erupted from its poles, carving cavities in the cloud. Within a few million years, the core of the protostar heated to 10 million degrees, and hydrogen nuclei began fusing into helium. In that moment, the star ignited its thermonuclear engine. Once nuclear fusion firmly established itself, the sun entered its main sequence phase. A long, stable period that would last billions of years. Its light scattered the remaining gas, leaving behind a disk where planets could form. This was the beginning of our star's life, forged from cosmic debris, kindled by gravity, and shining steadily at the center of a newborn solar system. But to understand how this star will one day swell and consume its inner worlds, we must first look beneath its fiery surface. At the center of the sun lies the core, a dense thermonuclear furnace heated to about 27 million degrees Fahrenheit. Here, under immense pressure, hydrogen atoms are fused into helium. Every fraction of a second, hundreds of millions of tons of hydrogen are transformed into new elements, releasing the energy that makes the sun shine, a process we'll examine more closely soon. The core extends to about a quarter of the sun's radius, roughly 100,000 miles from the center, beyond which its power begins to decrease. Surrounding it is the radiative zone, a vast inner shell where the core's energy radiates outward as photons. But these photons don't race straight to the surface. The radiative zone is so dense that each photon's journey is a zigzagging path. The quanta of light bounce from particle to particle, getting absorbed and re-emitted countless times. Though photons move at the speed of light, they're endlessly delayed. It can take a single photon around 170,000 years to seep into the next layer. In this deep, opaque region, energy creeps outward at a glacial pace. As we move farther outward, a remarkable transition occurs. Around 70% of the way from the sun's center, the temperature drops a few million degrees, and the density falls sharply. Here, the method of energy transport completely changes. We enter the convective zone, a turbulent outer layer about 125,000 miles thick. The solar plasma here is cooler, just 6.5 million degrees Fahrenheit at the base, dropping to about 10,000 degrees Fahrenheit at the surface. Cool enough for heavier ions to retain some electrons, making the plasma more opaque to radiation. Trapped heat causes the plasma to boil. Hot gas from below becomes buoyant and rises in massive plumes. Upon reaching the top of the convective zone, it cools and sinks again. This is a vast, churning ocean of plasma. Each upwelling plume is the size of a continent. By the time energy reaches this zone, it escapes much more quickly. Convection currents carry heat to the surface in mere weeks, not millennia. If we could hover just below the sun's visible surface, we'd see a rippling, grainy pattern, like a pot of gently boiling soup, with countless cells of hot plasma rising and cooler plasma sinking. In fact, these cells are visible from above. Close-up images of the sun reveal granules about 600 miles across. Their bright centers mark where hot plasma is rising, while the dark edges are where cooler material is descending. Each granule exists for only a few minutes before being replaced by another, as the star's surface seethes and roils. Closer to the surface, there's also a thin but important boundary that separates the radiative interior from the convective outer layer, the tachocline. This is a shear layer where the star's internal rotation changes abruptly. Deep within the radiative zone, the sun rotates almost like a solid sphere, with a period of about 27 days. However, the overlying convective zone rotates differently, faster at the equator, taking about 24 days, and slower towards the poles, around 34 days. In the tachocline, located at about 0.7 solar radii from the center, this mismatch in rotation speed creates intense shear. It is believed this is where the sun's magnetic field is generated, as electric currents in the conductive plasma amplify magnetic loops. In essence, the tachocline acts as the sun's magnetic dynamo. The churning and stretching of magnetic field lines in this layer creates a global magnetic field that permeates the star and governs its cycles. From this thin, invisible interface arises the forces responsible for everything from sunspots to solar flares. Rising upward through the convective flows, we finally reach the photosphere, the visible surface of the sun, the sphere of light we see with our eyes. Technically, the photosphere is not a solid surface at all, but a thin layer of gas about 250 miles thick. Here, the plasma density becomes low enough that photons can escape into space. Light, after a fantastically long journey from the core, is emitted from this layer and races out into the solar system. The temperature of the photosphere averages about 10,000 degrees Fahrenheit, much cooler than the inferno of the core, but still hot enough to make even metals glow white hot. This is the layer where we see sunspots, faculae, and granulation through telescopes. Sunspots appear as dark blemishes on the photosphere. They're significantly cooler regions formed by intense magnetic fields. The magnetism in sunspots suppresses the convective flow of hot gas from below, causing these areas to cool and darken compared to their surroundings. Sunspots often appear in pairs or groups with opposite magnetic polarity, signs of magnetic flux tubes looping out from within the sun. They may last for days or weeks. Some can grow larger than Earth. Around active sunspots, we often find bright plages and faculae, areas of concentrated magnetic field that make those regions of the sun slightly brighter. Meanwhile, the entire photosphere is covered in constantly shifting convection granules, each one a cell of hot plasma the size of Texas, continually forming and dispersing. Above the photosphere, the sun's atmosphere extends into two more main layers, the chromosphere and the corona. The chromosphere is a fragile region just a few thousand miles thick, located directly above the photosphere. Usually invisible due to the brightness of the photosphere, it becomes visible as a thin, ruby-red rim during total solar eclipses. Surprisingly, the temperature in the chromosphere increases with height, from about 7,000 Fahrenheit at the base to 14,000 Fahrenheit and higher at the top. This inverted temperature gradient remains one of the sun's most intriguing mysteries. The chromosphere is shaped by magnetic fields. It boils with dynamic jets known as solar spicules, which resemble blades of plasma shooting upward. Spicules are narrow, geyser-like eruptions lasting just a few minutes. At any moment, up to 10 million spicules erupt across the chromospheric network, reaching heights of 3,000 to 6,000 miles and speeds of 30 to 60 miles per second. They launch hot plasma into the outer corona and may play a role in heating it. When viewed through special filters, the chromosphere appears as a web-like network of brighter regions, highlighting larger convective cells known as supergranules. Above the chromosphere lies a narrow transition region only a few hundred miles thick, where temperatures suddenly skyrocket from tens of thousands to nearly 1,000,000 degrees. Beyond this lies the sun's outermost layer, the corona. The corona, named after the Latin word for crown, is a vast halo of plasma stretching millions of miles into space. During a total solar eclipse, the corona appears as a pearly white crown around the sun, with visible streamers and plumes shaped by the sun's magnetic field lines. In the corona, ions are so energetic that they emit mainly in X-rays and extreme ultraviolet wavelengths. Why the sun's outer atmosphere is so incredibly hot, far hotter than the photosphere beneath it, remains one of the biggest unsolved questions in solar physics. It's as if you moved away from a fire and the air somehow got hotter. A counterintuitive reality driven by mechanisms we don't yet fully understand. The layer has no upper boundary. It fades into the solar wind, a continuous flow of charged particles that spreads outward, enveloping all the planets and bodies in our solar system. This dynamic structure makes the sun not just a light bulb in the sky, but a living, breathing star. Yet to truly understand how the sun shines, we must dive back into the central inferno and study the engine at its heart, the nuclear alchemy that powers everything else. At the core of the sun and the crushing density and searing heat, an almost mystical process unfolds. the fusion of hydrogen into helium. Here, Einstein's profound equation, E = mc², manifests itself as mass is converted into energy. The dominant fusion cycle in the Sun is known as the proton-proton chain, a sequence of nuclear reactions that might sound like technical jargon, but is in fact the story of the birth of sunlight. Imagine two protons, bare hydrogen nuclei hurtling through the chaos of the core. Under normal circumstances, they would fiercely repel each other. Both carry a positive charge, and like two similarly charged magnets naturally push each other away. In fact, classical physics says that no proton in the Sun's core should ever get close enough to fuse, since the electrostatic repulsion is too great. Calculations show that at the Sun's core temperature, the probability of two protons overcoming this repulsion is essentially zero. And yet, the Sun shines nonetheless. The key to this apparent paradox lies in the subtle world of quantum mechanics. Protons are not just particles, but also waves, with positions blurred into a quantum haze. This allows for a phenomenon called quantum tunneling, where a particle can tunnel through an energy barrier it couldn't surmount classically. It means that in the Sun's core, it's extremely rare, estimated at one success per 10 to the 28th collisions, for protons to get close enough for their quantum wave functions to overlap and tunnel through the repulsive barrier. As if by quantum luck, the protons find a hidden path and merge. And when they do, something extraordinary happens. They fuse, forming a heavier nucleus. This remarkable encounter is the first step in the proton-proton chain. Two protons fuse, and in the process, one is transformed by the weak nuclear force into a neutron, resulting in deuterium nucleus. The reaction releases a flash of energy in the form of a positron and nearly massless particle called a neutrino. The positron almost instantly annihilates with a nearby electron releasing gamma radiation. The neutrino, a ghost particle, barely interacts with matter, so it escapes from the Sun's core at nearly the speed of light, carrying away a tiny amount of energy. Fun fact, every second, billions of these very neutrinos pass through every square inch of Earth and everything on the planet, including your body. Next, the newly formed deuterium nucleus doesn't linger. In the second step, it collides with another proton, forming helium-3. This reaction gives off a burst of high-energy gamma photons. And finally, in the third stage, two helium-3 nuclei collide and fuse, forming helium-4, a normal helium nucleus, and ejecting two extra protons that weren't needed in the final product. These free protons may go on to participate in the process again. The final stage also releases energy. To sum up the net result of the proton-proton chain, 4 protons ultimately merge into a single helium-4 nucleus, and in doing so, some mass is lost and converted into energy. The helium-4 nucleus has slightly less mass than the 4 protons that it formed. This missing mass becomes energy released as gamma rays. It is this transformation of mass into energy that powers the Sun, flooding the core with high-energy photons. On paper, this chain reaction may seem complex, but in reality, it occurs on an incomprehensible scale. In the core of the Sun, approximately 4 times 10 to the 38th protons fuse into helium every second. Translated into layman terms, this equates to hundreds of millions of tons of hydrogen fusing each second. The energy released from these reactions is staggering. The sun generates about 4 times 10 to the 26th watts of power, equivalent to billions of 1 megaton nuclear bombs detonating every second. But even in this case, for any individual proton, nuclear reactions are incredibly rare. Most protons bounce around billions of times per second without ever fusing. But the sheer astronomical number of protons in the sun's core means that even a tiny fraction of fusion events is enough to maintain this immense energy output. The high-energy gamma photons created in these fusion reactions begin an epic journey outward. At the moment of their creation, they carry the energy of the sunlight in its most primordial form. But as previously described, these photons must pass through the radiative zone. Gamma rays travel just a fraction of a millimeter before being absorbed by an ion in the dense solar core, which then re-emits a photon in a random direction. With every interaction, the photon's energy slightly diminishes. After countless absorptions and re-emissions, the original gamma rays are transformed into a swarm of lower energy photons. First X-rays, then ultraviolet, and finally, visible light. What ultimately escapes the photosphere is primarily visible and infrared light, the sunlight we know. It takes hundreds of thousands of years for energy to travel from the core to the surface in the form of light. However, once freed, it travels 93 million miles to Earth in just 8 minutes and 20 seconds. The light warming your face at noon may have originated in the heart of our star when early humans were just learning to harness fire. But the sun is not a quiet beacon. Its steady glow hides a restless temperament. From the surface to its outer atmosphere, the sun undergoes magnetic phenomena that can erupt with titanic force. Long before Galileo's telescope, ancient Chinese astronomers observed sunspots, the most visible indicators of the sun's magnetic disturbances. In these regions, magnetic field lines burst through the photosphere, suppressing the usual convective flow of heat. Here, intense magnetism reigns, measured in thousands of Gauss compared to the Earth's field of just 0.5 Gauss. As mentioned earlier, sunspots often appear in groups and, typically, in mirror image pairs of opposite polarity, north and south poles, magnetically speaking. Massive magnetic loops connect these polarities, arcing above the solar surface and trapping and guiding searing hot plasma. These structures are like temporary scars on the sun's face, marking regions of magnetic tension. And where there is tension, there may be violence. The most dramatic solar outbursts, solar flares, often occur in magnetically complex sunspot regions. A solar flare is essentially a stellar explosion, a sudden outpouring of energy when magnetic fields twist, shift, and suddenly reconnect. Within sunspot groups, opposite magnetic poles sometimes get pushed close together. If the magnetic field lines suddenly realign, a process called magnetic reconnection, an enormous amount of energy is unleashed in seconds. Think of it like a tension rubber band suddenly snapping into a new shape, sharply releasing its stored energy in an instant. Solar flares can heat material to tens of millions of degrees in minutes. X-rays and extreme ultraviolet radiation burst outward along with a flood of charged particles. The energy of a large flare is almost unimaginable. The most powerful flares can release energy equivalent to 1 billion 1 megaton nuclear bombs exploding at once. And we often observe this event as two bright ribbons in the chromosphere on either side of the magnetic neutral line, connected by loops of glowing plasma. Closely related to flares, yet distinct, are coronal mass ejections, or CMEs. A CME is an enormous cloud of solar plasma and magnetic field hurled out from the solar corona into space. They often accompany flares or filament eruptions. Imagine a giant loop or filament of magnetized plasma in the corona becoming unstable. It can break free and expel billions of tons of matter into the solar system. As the CME unfolds and expands, it can grow larger than the Sun itself, though the plasma inside remains extremely diffuse. CMEs race outward at millions of miles per hour. Some have been recorded at speeds of 1,200 to 2,000 miles per second, much faster than the average solar wind. When a CME is directed toward Earth, it becomes a matter of space weather. 1 to 3 days later, this cloud of plasma and its embedded magnetic field reaches our planet. This way, through flares and ejections, our star can directly affect Earth and our technological systems. When fast-moving charged particles and magnetic shock waves from the Sun collide with the Earth's magnetic field, they can trigger geomagnetic storms. The most harmless result of such a storm is also the most beautiful: the aurora. Aurora borealis in the north and aurora australis in the south hemisphere occur when energetic particles spiral along Earth's magnetic field lines and crash into the upper atmosphere, causing the air to glow like gas in a neon sign. Green curtains of light appear in the polar sky, sometimes joined by reds, blues, and purples, a direct visible reminder of our star's tantrums. But solar flares can have more dangerous consequences. Strong geomagnetic storms can disturb the ionosphere and upper atmosphere, disrupting radio communications and GPS signals. They can induce harmful currents known as a geomagnetic induced current, GICs, and long conductors like power lines and pipelines. For example, a powerful solar storm in March of 1989 caused massive GICs that knocked out the power grid in Quebec, Canada, plunging millions into a 12-hour blackout. Auroras from this storm were seen as far south as Florida. Looking even further into the past, the strongest solar storm in recorded history, the Carrington event of 1859, caused telegraph wires to spark and even ignited fires in telegraph offices. Scientists warned that if a Carrington-level event struck Earth today, it could wreak havoc. Widespread power outages, satellite damage, navigation failures, and radio blackouts. Our modern technology-dependent civilization is far more vulnerable than the world of the 19th century. In 2012, we had a near miss. A Carrington-scale CME erupted from the Sun, but fortunately, Earth was not in its path. It swept past our orbit, missing us by just a few days. Had it struck, we would be remembering the storm of July 2012 as a catastrophic event. Solar flares and Earth-directed CMEs together can affect satellites, astronauts, airlines, and power infrastructure. Intense radiation and bombardment by charged particles can short-circuit or even permanently damage satellites. The magnetic field of a powerful CME can also compress Earth's magnetosphere and generate currents that fry power grid transformers. Even at moderate levels, solar activity increases atmospheric drag on satellites in low Earth orbiting by heating the upper atmosphere. For example, a relatively small geomagnetic storm in February 2022 caused dozens of newly launched small satellites to fall out of orbit and burn up as they encountered denser air than expected. It's also worth noting that astronauts outside Earth's protective atmosphere, on the ISS or in future missions to the Moon or Mars, are also at risk from radiation surges during such events. becomes clear that monitoring solar weather is not just an academic exercise, it is crucial for safeguarding our technological infrastructure. To the casual observer, the sun's activity may seem random or episodic. But by studying the sun over decades and centuries, astronomers have uncovered a surprising pattern. The sun goes through cycles of high and low activity, much like seasons in an astronomical year. This is most evident in the ebb and flow of sunspots. The number of sunspots increases and decreases in a cycle that averages about 11 years. At its peak, the solar maximum, hundreds of sunspots may pepper the star over the course of several weeks. At the minimum, the sun may appear flawless for days or even weeks. This pattern was first noted by Samuel Henrich Schwab in the 1840s. And since detailed records began, it's held true. Today, we call it the 11-year solar cycle or the Schwab cycle. So during their solar maximum, the star is magnetically most active, causing more intense space weather effects. And paradoxically, despite the presence of dark spots, the sun's overall brightness in visible light slightly increases. The brightening from surrounding faculae outshines the dimming from sunspots, making the star about 0.1% more luminous. The corona during solar maximum becomes alive with streams and flows, and auroras tend to occur at lower latitudes due to more frequent geomagnetic storms. So what drives this cycle? Scientists believe it's related to the recharging of the sun's magnetic dynamo. Roughly every 11 years, at the peak of the cycle, the sun's magnetic field flips. Its north and south magnetic poles swap places. To be precise, the solar cycle is actually a 22-year magnetic cycle called the Hale cycle, since it takes two 11-year cycles for the sun's magnetic polarity to return to its original orientation. During each cycle, sunspots first appear at mid-latitudes, then gradually cluster closer to the equator. This pattern is known as Sporer's law, and it's often visualized in the famous butterfly diagram, which depicts sunspot latitudes over time. The cycle isn't as precise as clockwork. Some cycles are slightly longer or shorter, ranging from 9 to 14 years, and vary in intensity. Sometimes the sun experiences unusually quiet periods that last for multiple cycles. For example, during the Maunder minimum in the late 17th century, almost no sunspots were observed for about 70 years, coinciding with a cooler climate period on Earth known as the Little Ice Age. In contrast, the current cycle, Solar Cycle 25, seems to be ramping up with a surprisingly high number of sunspots, indicating a vibrant maximum. For Earth and our technology-forward society, the solar cycle acts as a rough clock of space weather risk. During solar maximum, governments and satellite operators remain on high alert. And while the sun is quieter during solar minimum, that doesn't necessarily mean it's safer. One side effect is that more cosmic rays, high-energy particles from distant supernovae, can penetrate the inner solar system, since the weakened solar wind provides less shedding. This can pose risk to astronauts and high-altitude flights, especially over the poles. However, even beyond the sun's internal cycles, external influences can alter the fate of our solar system. Let's not forget that we are constantly drifting through the galaxy, and the gravitational pull of passing stars can disturb the delicate clockwork of planetary orbits. Recent research has shed light on just how unstable the long-term stability of our system might be when broader galactic forces come into play. Over billions of years of its existence, the sun has not been stationary. It orbits the center of the Milky Way, oscillating up and down through the galactic disk as stars have formed and vanished around it. From time to time, another star passes near our system. In cosmic terms, this might mean a few light years away, and in rare cases, less than 1 light year. On Earth, we may not notice anything during such a distant pass, but the outer regions, such as the Oort cloud of comets, can feel the tug. But what if a star came closer? Astronomers and dynamicists have long studied the stability of planetary orbits. On their own, the planets interact in a delicate gravitational balance that remains mostly stable over the Sun's entire lifespan. Although there's a tiny chance that internal chaos could knock Mercury or Mars off course over a billion-year timescale, even without external influences. That's not the focus today. As we know, the solar system is not an isolated island. We live in a galaxy teeming with stars, and with enough time, the odds of a close stellar encounter increases. Recent research is aimed to determine how such stellar flybys could influence the future of our system. The findings inspire both awe and concern. In a 2025 study, scientists simulated the next 5 billion years of our system's evolution while factoring in the gravitational nudges of passing stars. They ran thousands of simulations, varying random stellar encounters based on current knowledge of the galaxy's stellar density. The results suggest that earlier models, which ignored passing stars, may have been too optimistic about the solar system's long-term stability. Passing stars, even relatively small ones, a quarter of the Sun's mass, at distances less than 100 astronomical units, can give the planets tiny nicks that accumulate or trigger chaotic consequences. In some cases, these disturbances are minor, but some simulations show that a close stellar encounter could drastically alter the solar system. How drastically? A study showed that the presence of random passing stars could increase the likelihood of planetary instability several times over. For instance, tiny Pluto, which remains stable in isolated models, has about a 5% chance of being ejected or colliding over the next 5 billion years when stellar flybys are included. Mercury, already the most vulnerable planet due to internal chaos, sees its destabilization probability rise by 80% under stellar perturbations. In practical terms, this means that the baseline, less than 1% chance of Mercury eventually crashing into Venus or the Sun, increases to 1.8%. Still small, but not insignificant. And the surprises, they don't end there. Simulations indicate that Mars has a 0.3% chance of being ejected from the solar system or colliding with another planet in the next 5 billion years. For Earth, the probability of being ejected into deep space or undergoing a catastrophic collision due to the cumulative disturbances is around 0.2%. It's a small number on the scale of 5 billion years, but still, the probability is not zero. In fact, it's a sobering figure, roughly a 1 in 500 chance that before the Sun's lifetime ends, Earth's orbit could be destabilized by an external stellar influence. Perhaps even more astonishing is that when such instabilities are triggered by passing stars, they tend to cause multiple planetary losses and occur earlier than in isolated simulations. In many cases, if a truly close stellar encounter occurred, imagine a star coming within 100 astronomical units or thereabouts. Chaos could unfold within the next 1 to 2 billion years, not 4 to 5. At this kind of distance, the peaceful clockwork of our solar system, the stable orbits we take for granted, could unravel. The Oort cloud of comets would almost certainly be disturbed, sending comets inward. Researchers noted that the probability of a star passing closer than 100 AU, which is approximately twice the radius of Pluto's orbit, within the next 5 billion years, is about 5%. And if an encounter like that occurs, all bets on long-term stability are off. Yet, even as we ponder these distant possibilities, the Sun continues to astonish us here and now. With ever-advancing telescopes and observatories, we're unveiling layers of its behavior on the smallest scales. Most recently, a groundbreaking discovery showed that even the Sun's quiet surface harbors an unexpected fine structure we could have never suspected to exist. In pursuit of deeper understanding of the Sun, scientists built the largest solar telescope in the world, the 13-foot Daniel K. Inouye Solar Telescope in Hawaii. In 2025, during its first observing campaigns, the telescope achieved a stunning feat. It captured the sharpest view of the Sun's surface ever recorded, revealing ultrafine magnetic structures just 12 to 30 miles wide. For reference, 12 miles is roughly the length of Manhattan, minuscule on the solar scale, which spans about 1 million miles. These tiny magnetic striations were seen rippling along the edges of solar granules, appearing as alternating light and dark threads tracing the walls of convective cells in the photosphere. What are these striations? The research team explains that they're caused by sheet-like curtains of magnetic field protruding through the granular boundaries. When hot plasma rises within a granule and descends in the neighboring downdraft lane, the magnetic field can form a vertical magnetic curtain. Light passing through these curtains is modulated. If the magnetic field is slightly weaker, the light appears slightly darker. If stronger, slightly brighter. The result is a pattern of bright and dark stripes along granule edges, revealing subtle changes in magnetic field strength over just a few dozen miles. In essence, a magnetic fingerprint on the smallest scale we've ever directly observed on the Sun. Although there have been hints of these features in high-resolution magnetic simulations, they've never been observed until now. These magnetic curtains could affect how energy moves upward through the solar atmosphere into the corona. And the fact that solar magnetism has such microstructure may hold the key to solving larger mysteries. Small-scale magnetic fluctuations might collectively contribute to chromospheric or coronal heating or spark larger eruptions we observe. The Inouye telescope team emphasized that understanding this fine-scale magnetic architecture is vital for better forecasting space weather. Yet, even as we decode the Sun's present-day behavior, we're also gazing into its future. What fate awaits our star when it runs out of fuel? The coming chapters promise to be dramatic and possibly quite harsh for the planets in the solar system. As of today, our Sun is in the middle of its life cycle. It resides contentedly on the main sequence, steadily fusing hydrogen in its core. But eventually, as with all stars, it will run out of fuel at its core. And when that happens, the balance it maintains will break down. About 5 billion years from now, the core will have exhausted its hydrogen, turning it into helium ash. And after that, a dramatic transformation will occur. When hydrogen fusion ends, the core will begin to contract under gravity, since the outward pressure will drop. This compression has an interesting effect. It actually heats the core even more. Meanwhile, just outside the core, in a shell of hydrogen that was previously not hot enough, the rising heat ignites hydrogen fusion. So, while the inert helium core shrinks, a thin shell around it suddenly becomes a new energy source. Shell fusion actually releases more energy than core fusion did. The extra energy causes the Sun's outer layers to swell. Our Sun will become a red giant. So named because as it expands, its surface cools and its light shifts toward redder wavelengths. Over a few tens of millions of years, the sun's radius will increase by dozens, then hundreds of times. And at its peak, the sun may reach a radius of about 1 astronomical unit, the current distance between the sun and Earth. In this scenario, Mercury and Venus will undoubtedly be swallowed by the bloated outer layers of the star. Earth's fate is less certain. Some calculations suggest it might narrowly escape engulfment, residing within the sun's expanded atmosphere, but others indicate that friction with the star's outer gases and orbital decay will pull Earth inward in a spiral until it vaporizes. Either way, the outcome will be grim. Long before the sun physically engulfs Earth, its increasing brightness will boil away the oceans and strip the planet of its atmosphere. During the red giant phase, the sun's helium core continues to contract and heat until it reaches a critical threshold. When temperatures hit around 100 million degrees, helium fusion ignites in the core. In a star like ours, this occurs in a dramatic event called the helium flash, a sudden explosive onset of helium burning into carbon, lasting only a few moments until the core expands and cools again, reaching a new equilibrium. Afterward, the star will peacefully burn helium in its core for the next 100 million years, converting it into carbon and oxygen, becoming somewhat smaller and more blue in the process. When the helium supply is exhausted, the sun will not be massive enough to ignite carbon fusion. The core will contract once again and the star will swell a second time, but this time even more dramatically. The sun will become enormous and unstable. During these late stages, it will shed much of its mass, up to 30%. Pulsations and strong stellar winds will blow away the outer layers. In its final throes, our star will completely cast off its outer shell. The hot, exposed core, now a compact object the size of Earth, it will flood the surrounding expanding gas with intense ultraviolet radiation, causing it to fluoresce. This is the creation of a planetary nebula, a somewhat misleading name, a remnant of history for these glowing shells of gas around dying stars, since they have nothing to do with planets. Our sun will release into space its own stunning nebula, like a shell or series of shells of multicolored gas. Over tens of thousands of years, this nebula will expand and illuminate the local interstellar medium. And yet there is certain beauty in knowing this. We stand on Earth beneath the light of an evolving star, a star that links us to both the beginning of the universe and the end of our solar system story. Every calcium atom in our bones was forged in the heart of some star. Every photon that paints leaves green was released from the sun's furnace after centuries of imprisonment. We are truly children of the sun. And as long as it continues to shine, life on Earth has a chance to thrive and to astonish.